嘉宾是来自纽约市立大学电子工程系和计算机科学系的特聘教授，田英利老师。他具有多种专业背景，先后学习精密仪器与光电工程学、热物理工程学、电机工程学等多个专业，并在卡内基梅隆大学机器人研究所、IBM Watson 研究中心带领团队多次获奖。2008年，田英利老师加入纽约市立大学，专注利用计算机视觉和机器学习等技术帮助老年人、视障、听障等特殊人群，并当选美国电气电子工程师协会和国际模式识别协会的两会会士。他今天给我们讲的报告是AI-driven Automated Medical Image Analysis。让我们掌声有请田教授。
Thank you, Professor Xu. I saw in our audience we have a gentleman there, so I will still keep the talk in English. Today's talk will focus on medical image analysis. This is only one small part of my research. My main research is about the computer vision, focus on the human behavior analysis, and also apply that to the assistive technology, just like Professor Xu introduced, which include the how to use the computer vision technology to help blind people or other people who has the special needs, such as deaf people for the American Sign Language. Okay, so I will start. Let's see. Okay, so I think for the medical image analysis, I started this research several years ago because of family reason. So here, from the figure, you can see most of the medical images, I think everyone experienced that. If you didn't experience that, you are really lucky, okay? So for the MRI, ultrasound, X-ray, and also CT, PET, mammogram, all this, right? It's involving our daily life. But how can we do it by apply the AI-driven things to really help, I think, both the doctors and also patients to get those kind of, analyze in a more accurate way and also to do more accurate diagnostic. Just as Professor Xu's question to Dr. Chen is still far from the 100%. I think it will never be 100% because for the different patient situations, all change and it's all progressive. If the AI can really achieve the accuracy for the well-experienced, our well-trained radiologist, our pathologist to that level, then the AI method will be widely used in all the systems. It's already being used in many applications, but for the medical, images, it really depends on the accuracy compared to the experienced human, our doctors. My son is a doctor. I discussed this question with him. I asked them, do you think the radiologist will lose their job when the AI is really in that level? He said, no, will never. Do you really trust a machine diagnose your, situation? He said, in that case, if AI can do really good job, so the doctors can see more and more patients. And also for now, you see, even for the cancer screen, they only apply to some specific patients. They will not do for everyone. But if the AI can do that, the more people can do the early screen, so we can really reduce the death rate, especially for lung cancer. So I'll start, to say most of the AI-based medical image analysis now concentrate on 4, categories. I put in there. So the first one is the sensor size, mainly includes the image registration or the medical image translation. For example, for those kind of expensive, scans, for example, people how can transfer MRI images to CTs or something like that. Also for the detection, this mainly try to use the images automatically detect those kind of abnormal, regions or tissues so we can do the further diagnosis. Then people also can do for the segmentation. How do you segment the organs or the abnormal regions from the other tissues? The last one will be diagnosis. That's the real part will help the doctors to make it. Okay, so in this case, since we just started several years ago, so I want to share our studies for two topics. One is how can we do the virtual, contrast enhancement. That means without use those kind of, contrast dye, can we do the AI synthesized contrast image? So in that case, for the patients who has the kidney disease or the kidney dysfunctions, can we really help them without doing that, but still get the contrast images? The second one is about the AI-driven automatic cancer diagnosis. I will focus on two things. One is the lung cancer, and another one is the kidney cancer. Depends on the time. Okay, I know everyone's hungry now, so I may skip a part of that. Okay, so now let's move to the virtual contrast enhancement from CT scans. Here you can see for many diseases, patients will get those kind of contrast dye to highlight their inner organs. But for some patients with the kidney disease, it's really hard. We'll get the really the serious the dysfunction for their, for their the allergy things, for their, kidney things. And also some doctors may try to reduce the dye, but after you reduce the dyes, they may also reduce the highlights of the organs. Then that will need the repeat, the injection, which will even worse, okay? So in that case, we tried to develop AI methods to say how can we really do the, eliminate the dye, the injection. Here is what we want to do, We generate the idea to say, okay, how can we generate from the CTs, from the non-contrast, from the non-contrast CTs to generate the virtual contrast. Then we compare with those kind of real contrast CTs about that. So here I used two different kind of terms. One is a pre-contrast CT. That means for the patients who really get the inject. So just a before and after. For the non-one, that's totally the patient CT without that, just compare with the virtual CTs. Here in that case, most of the existing method for the virtual contrast CT only focus on MRI images and only focus on the brain image. But however, our the method focus on the abdominal and the pelvic, this part. Compared to the brain, this part will be more challenged because when patients lay on the CT machine, the position is changed and also the inner organs will change. So that will cause the much bigger misalignment between different kind of scans. So in that case, we have to handle the the misalignment and also compare with the brain features. Our inner organs of this part will have much more complex features. So how can we extract that so can get both detailed texture and also the global the alignment well. So here we propose the detail-aware and dual-path contrast enhanced framework. So in that case, we have the non-contrast CTs here. For the global path, we input the whole CT, the whole volume in there as the input. For the local path, we cut the the images to the 4 grids. Then we try to focus on more detailed features. Then we fill them together to get the predicted virtual contrast CTs. Also, I think because the big alignment, doesn't matter how hard we try for the pre-processing, we still have the large misalignment there. So we tried to use the perceptual loss function to handle it so we can get a better result for that. I want to just to show you for the data set we use total 65 patients for that. It's pretty small data set. I think that's one challenge for the medical image processing compared to the large language model and also computer vision large, just like recently for the segment anything, that's also pretty general model. So also because of patient privacy, they're not that large data set shared for the medical image. I hope someday we can have the big enough data set so we can train the general medical model. Then for each different kind of specific application, we just do the fine tune. So that's I think will happen in future after we remove the patient's private, the identity information. So you can see here in our method, we are not only handle one the contrast phase. We have the pre-contrast CT, then we have the 3 phase of the the highlight. The first one is the arterial. That's just after you inject the dye, we will scan it. Then after a little while, we scan another one, that's a portal phase. And also we have the delayed after several minutes. For each of these phases, different kind of organ will be a highlight. So our method will try to handle all the different kind of phases by the single framework. Okay, here, I just want to show you here. The first row shows you all the non-contrast CTs. The second row shows you the real contrast CTs. The third row is our CTs, the virtual contrast CTs. You can see compared to the ground truth. Pay attention to the fourth row. You can see it's very close to those kind of real contrast CTs. We also tried the cycle gun of the different kind of loss functions and also the contrastive loss. You can see for the main part, some of them cannot be really highlighted. Okay, we also evaluate our method by 2 radiologists in the blind review. That means we send them the different kind of contrast CTs without tell them which one is the real contrast, which one is generated by our method. So you can see why the radiologist 2 like our system much better than the radiologist 1. So we evaluate it in 5 scales: poor, suboptimal, acceptable, good, excellent. So you can see we get the average about the score 3. That means acceptable. But still, there are far way to go. I want to show you some of the the limitations. Most of the limitations we cannot handle as we create the patchy enhancement. That means for the whole part should be highlighted, but the virtual CT only highlight a part of that. Or also for some part, the real CT, contrast CTs are highlighted, but we miss it. But sometimes it will also generate unnecessary enhancement. So that's the part we really need to improve that. And just to quickly summarize this part of that, we are the first one to generate the virtual contrast CT for the the abdominal and the pelvic region of that. We are also the first one to use the single framework to handle the multiple contrast phases. For the future work, we want to really do not only for that, axial CTs, they have the different kind of, projections. We may also include them. Also, I think for now, if we have more data, how can we use field data to fine-tune it? That's the active learning and the field shot learning for that. I'm also thinking the basic thing is not only say how similar the virtual CT to those kind of real contrast CT. We do this kind of contrast mainly want to do the downstream task test. That means how can we really do for the cancer detection or some abnormal detection. If the virtual CT in the downstream task can achieve similar result for the real CTs, then I think we finish the task. We don't really need to get really similar of those kind of, image as the real contrast city. Okay, so let me move to the next topic. That's the AI-driven automated diagnosis for, lung nodule detection. I lost my husband for the lung cancer. That's also when we visit the hospital, so many times I built the connection with the doctors. That's why I started this research. Okay, so lung cancer, everyone now is the first killer for the cancer. And also most of the case, when it's diagnosed, it's already the stage 4, so we really want to do something. If we can do the cancer, our nodule detection at the early stage, then what we can do, right? So in most of the existing methods only use the 2D detection networks. Sorry for that. They only use the 2D networks without use the temporal information for that. And some of them just use the 3D detection network, but with not that high enough, sensitivity and specificity. We can simply, understand the sensitivity. You can see simply as the, the precision, okay, the accuracy. The specificity, mainly you can think it's about the level of the false positives. So we want to really combine that, okay. So in that case, the remaining issue are still miss the detection on small nodules and also with much low specificity. That means we'll generate much more, high false positives. We don't want that to happen because the following up treatment will depend on the detection. If there is no nodule, you say, okay, there's a nodule, then maybe biopsy or those things are really unnecessary. We don't want the patient to suffer that. Also, it's low robustness. That means for different kind of scan machines or different systems, if you train your system on specific data set captured by some model of the CT machines, then if you test your method on other data, then the accuracy will decrease to a lower level. So can AI method help to accurately detect the lung nodule and reduce the false positives? So we tried that. We designed the method. We call it the 3D feature parameter network, and then followed by another false positive reduction network. It's really amazing. For those kind of nodule and tissues, if you only observe them from especially for the false positives, only focus on the small region, you cannot see difference. Here, I just want to show you one compare of them. Those are the real nodules, but that one are the false positives. But when we really protect them by use several slides, use the local image history, then our network can really reduce them dramatically. So in that case, we really can create a very low, very low false positive. Instead of only use that small data set, we also proposed to use the self-supervised learning to really learn from the larger data set. I think they have the NIH collected the early lung cancer screening for those kind of cities. Without use any ground truth, we just rotate those kind of images to 90 degree, 90 degree, 90 degree, then come back. Because we rotated them, we know which degree it is. So we just train the method to learn, okay, what's the degree of the image we rotated. Then in that case, we learned the pre-trained model for the feature learning. Then we apply those kind of features to initialize our model, which largely improved the result. Here, I just want to quickly show you some of the visualization results. You can see our method can handle very small nodule, about 3 millimeter, to the larger one, about 30 millimeter. So the whole data set, the maximum, the largest size is about 30 millimeters. Okay, here are the, the more detailed result. We compared it with the state-of-art result. We also tested it based on those kind of, different kind of, you can see here, we use the, FROC, that's a free response receiver operating characteristic method about that. So one of is that's all based on the false positives. That means for per scan, per CT scan, how many of the false positives we can detect it or are allowed. So you can see our method achieves very high, scores. We also evaluate that with our result, those kind of, different kind of, the reduce of the false positives. You can see it's really doing very well. And here also we tested the robustness across different kind of data set to see how well it will perform. Without any return or return, you can see the performance keeps pretty good. So it's pretty robust. Okay, quick summary about this part. So we focus on really reduce the false positive, and also we did very good. And also the self-supervised pre-trained model also improved the result a lot. Okay, so now we just want to, since this part we did really good, and also we know for the CT scans are projected to different kind of access. Then our next idea, can we don't use those kind of projections, the CT images, but instead of use the CT images, can we really use the the 3D point cloud? Here we tried, you can see here, compared to the CT images here, for the CT point clouds, we have the geometry invariance. You can really do the multi-perspective projection, and also we have the real, world coordinates about that. It can handle irregular shape, but we don't have the grid alignment. But for the 3D point, we couldn't get the texture features. Those are the drawbacks. But we have all other advantages of the CT images. So in that case, we apply the the point cloud directly and project it in, I'll skip this because of time. So we propose this framework. We project the 3D point cloud to N wheel samples. In our research, we did the 4 wheels, but we want to do extend it to multiple wheels. So I'll skip the details about that. Here are our result. We did pretty good for get the comparable result with the state of art, but still for the accuracy, it's still lower than the framework we talked before. Mainly, it's like the accuracy for the detection of the very small size of the lung nodules. So the previous framework we talk can handle the small nodules much better. So we will think about how can we really go to the more local features from the 3D point. Okay, so I'll skip that. So we'll quickly go to the diagnose for the kidney and renal mass segmentation and the classification. This one combines the segmentation and the classification. The segmentation means when you give the CT scans, we need to segment the kidney regions and also the nodule regions. After we detect the nodule regions, we want to continue to do the classification for which type of the nodules, because different kind of nodules have the different kind of, the progress. So the doctor needed to do that. So in this kind of things, we have 2 frameworks. For the framework about the 3D segmentation, we have the 3D CT impulse. Then we segment the regions and also the nodule. We crop that small regions. Then we input the small regions then into that classification network. Then really can separate, classify the subtype about that. Okay, here are our results. You can see for the first table shows you the segmentation results. Our method compared to the state-of-art result, we achieved very good result. The bottom table shows you the subtype classification result on one data set about that. We achieved 80%, more than 80%. So Dr. said that's comparable with the human radiologist for that. Okay, here we also try to, how can we improve the result? So we tried the weekly supervised classification. That means for the classification, without really use all the annotation for all the frames. We just use for the nodule part, the first slice, and also for the slice with the bigger size, the bigger size, and also the last slice of the nodule. Only use 3 slides. You can see we can improve the result. We can improve the result. The first row shows you without the weekly supervisor training. The second row shows you with the supervisor training. You can compare the numbers. Even with only 3 slides per CT scan, we can largely improve the result. Okay, so I think here are the quick, visualization result. You can see in the orange, the red one, that's the kidney. In the blue ones, that's the, the nodule, the cancer, the nodule. Also, quickly summarize it. We developed the framework can handle the segmentation and also the subtype classification, and also by only use several slides for the weekly supervised can largely improve the result. Before I finish it, I just want to quickly summarize our, predict what we needed to do in our future. I think most of people, especially for the large general, the model available, I really think we will have the large general model for medical image processing. And also, as Professor Xu mentioned, the field short learning and also cross different kind of domain will be another trend of that. I think if we couldn't get a good result, I'm still promising at least that means I still can keep my job, can continue doing this direction, right? Thank you very much.
All right, any questions? Yeah, I have a question, yeah. So in your case, so for people have of course a slight variation of our organs, but by and large, one organ has a somewhat standard structure. So I'm wondering whether it is possible to use this so-called model-based approach, let's say, for example, so-called structure-aware deep learning or topology-aware model, so that you can incorporate organ models in this process.
Yeah, I think that's another direction. Even for the lung nodule detection, there are so many other methods. First, detect the lung first. So in that case, we don't need to focus on other organs. So okay. That's the trend. People are also doing that. Yeah.
Okay, thank you. Any other question?好，那我们再次感谢那个田老师的精彩报告。好，我们这个 session 就到此结束了。今天下午呢还有很多的精彩报告哈，有 Web 3.0与 AI 的终极对创，多模态大模型与跨境电商，从 GPT 爆炸中诞生的 SaaS 等专场，请大家关注。好，今天感谢大家带到现在哈，也感谢今天分享的嘉宾，好，谢谢大家。